And that's where we're playing off of each other. Yeah, so this is like the Spencer sequences, right? And a lot of hay was made of playing with these sequences and learning things about them back in the 50s and 60s. But interestingly, this theorem was stated, 30 years earlier than that, or actually more, half a century earlier than that, where Cartan, I don't know if you've ever tried to read Cartan, but he just has this amazing way of just sort of discussing things casually and coming up with a wonderful theorem. And you're like, wait, what happened here? And he just knew, he didn't have cross minds, he didn't have, he hardly had the notion of ideal or anything. He was just pushing around symbols, and it just worked all the time. It was amazing. But anyways, this is sort of the formalization of this observation. So what this is really saying, and the reason this makes sense, is what you do is you look at this tableau and you say, suppose I only use the sort of first generic independent variable, right? And so we've used sort of generic coordinates to write this. How many conditions have appeared on the second derivative? So if I'm looking at a system, say, of first order PDEs, and I say, let's look only using dx1, ignore everything else, and I ask, how many conditions do I have to solve to go from dx1 to dx2? That's a bunch of second order conditions. And that's a bunch of things commuting. So that is S1. And then how many things do I have to check going from dx1 and dx2 to dx1, dx2, and dx3, right? So each time I add a new variable to solve an initial value problem, I'm adding on more conditions to check. Dimension of A1, this by construction, this is the number of variables that have to be free in the end. So I guess I may say it differently. So what you're doing is you're basically counting the code. You're counting the dimension of the solution for each iterative step of building your local solution. And if the total number of equations you came up with is the same rank as the size that you expect, then it must have worked. In other words, there are no hidden conditions, right? All the conditions for finding a solution are contained in checking the next derivative up. If that doesn't work, you prolong again and try again. If that doesn't work, you prolong again and try again. And there's a somewhat flimsy theorem that says that after sufficiently many prolongations and verifications of this form, you'll stop. Either you're guaranteed to find a solution of this form, or you'll show there is none. Yeah, one of the two.
That's when you have involutivity.
So this condition here is usually the definition of involutivity, right? So the theorem, this thing called the Cartan-Kuranishi theorem, is that it has very, very technical hypotheses about projections of different bundles and making sure that different things compose this diagram. But overall, it's saying that if you start off with sort of a well-posed PDE in the first place, in the sense that it's actually defined on a manifold, and prolongation, as long as prolongation makes sense, which is very hard to write down, as long as prolongation makes sense, and as long as the ideal you write down I is finitely generated, which is a reasonable thing for a PDE, I think, you don't want infinite family PDEs, then this process of prolongation and verification, this prolongation and check this condition, prolong, check, either you will at some stage, so there's a finite number at which either you prove there's no solutions, or you have found that it's involutive and therefore you've parameterized the solutions. So that's the Cartan-Kuranishi theorem in a nutshell.
Now, how do the R constants appear?
Oh, that's just the number of in this example the R was 3 because it was the 1, 2, 3 rows. So it's the number of sort of dependent variables you're using.
Okay, so you just got to set each guy for you.
So you set the dependent variables. Right? The way Cartan thought about this is Cartan didn't think about manifolds. He didn't think about, well, he probably did, but the way he worked was he worked on graphs. So he's saying I've got a space V and a space W. I'm trying to build a graph. So I have to pick a constant, which is the height, and that's how high is it on the graph? It's the number of dependent variables, W, right? And then I have to decide which angle I'm going to go, how many things I get to choose there. Well, I get to choose these number, and then figure out if you have the right number of linear conditions. So, Cartan didn't even use the word analytic anywhere, right? He just said, hey, I wrote down a solution, so it must be right. Yeah. If you look very carefully, he probably worked in the category that we would now called sort of like micro-local, like you work micro-locally on analytic stalks of the, yeah, so anyway. So many authors would say this is the definition of involutivity, this formal algebraic condition.
So do we have any relation between this equation at each level, A1, A2, A3?
Yes, in fact, you can compute, so what's the right way to write this? So you can think of,
For example, do we have a bound on the iteration that you have to go before?
that's an interesting question. Well, there's one sort of obvious and almost useless statement, which is that we're on a manifold of dimension n, or of dimension r plus n.
Right.
So eventually this just stops because we're running out of wedges. I think that some people, I think that Mark Green in particular has some sort of rough estimate. You know, basically the length of the let's see here. So, because of the, what's it called? Is it called the Hilbert lemma for syzygies, where you like it terminates at a certain minimal length? So if you're doing, so this is really about resolution of modules of your sort of,
regularity.
yeah. So the
regularity.
yeah, the sort of the length of the minimal sequence of syzygies to resolve a module can be estimated using things like Grosvenor bases, right? So you could do all that this way, and a few people have. So yeah, but I'm not an expert in that language so much. So. But yeah, all that sort of thing. Once you see that you have a long exact sequence of anything, you start thinking, well, you know, what can we use here? And you're trying to resolve some modules, so whichever way you want to look at it. Okay, so all of this is, everything I've written on the board now is at least 50 years old now. I want to sort of point out that this is, let me make an analogy here. So, actually I'll just say the analogy is going to write down. Okay, so here's an analogy from pre-calculus. We just defined the circle. The circle is all the things that are length 1 from the origin. So sort of description of what we're looking for, right? That's like saying involutivity is P's we can solve by power series. We have a condition we can check on a point, which will tell us whether it is or is not on the circle, right? We can do x squared plus y squared equals 1. We can guess x and y randomly, plug them in and check it and say yes or no, and do some sort of like random sample of the plane to sort of estimate what the circle looks like, right? That's essentially what this gives us. If you give me a PDE, I can check it. That's no problem. But there's something we can do that's much more powerful, right? We can say, I can make the circle by constructing the functions sine and cosine and say that x must be cosine theta and y must be sine theta. So the question that really kind of started to catch my attention about a year and a half ago was, is it possible to actually construct the involutive PDEs, right? The involutive tableau, actually. It's really an algebraic question. So instead of saying, here's a tableau, is it involutive or not? Does this condition hold or not? The question is, can I build them, right? I'll pick the dimensions a priori and say, can I actually write down the conditions that must be met? And the answer is yes. So to do that, I have to draw a few pictures, and luckily at this point, it's less sort of formal and more drawing things. So the idea is that the tableau in generic coordinates looks like this. Okay. And by the way, I should say, I'm about to discuss here, so I think it's 68 or 65, I think it's 68. Might as well check since I have it right here. Yes. And this was just a paper called Some Algebraic Aspects of Overdetermined Differential Equations. It's a very nice paper which establishes several basic facts about why these ideals are actually useful and what I haven't brought in the characteristic variety yet, but I will momentarily. And then the next and that paper was used for some things involving topics like Lie pseudogroups and G structures and very sort of formal differential geometry. And then it was sort of not used for very much because, I think mainly because although Guillemin had really great results that were sort of formal, there was nothing you could actually compute out of the paper. It was sort of like formally such a thing exists. The next thing was Dean Yang, who was down at NYU Polytechnic. So he used to work in this field, and actually his thesis was on extending C omega to C infinity in the mid-80s. But this was in 83 or 85. I don't want to make him feel old, but I guess he's not here anyway. I don't remember, it was in the mid-80s, sometime after it was 83 or 87 or 85. And so he studied what this condition was algebraically, because he wanted to change from using Cauchy-Kovaleska to using overdetermined to using hyperbolic C infinity theorems. So you want to use existence of solutions to hyperbolic C infinity first order systems, and then his thesis was exactly doing this, where he stated the sort of hyperbolic theorem for first order differential equations correctly, so he could reprove Cartan-Taylor using it, and then he gets this for free. And so he has this thing with C infinities everywhere if you check the initial hyperbolicity hypothesis. And then I guess the next thing is this paper that I'm sort of going through, which is that I guess it was on the archive last year. It'll be published probably in a month or two. And so there's some back some revisions next week actually. So that's sort of the history of this, and I'm hoping that because I have a very clear result, which is like, here is the ideal, that then people who are experts at, say, numerical algebraic geometry, or use Macaulay a lot for computing, for computing all sorts of things with ideals, suddenly we can learn a lot of things about PDEs that sort of were inaccessible before. So let me sort of just summarize how this whole thing works, and that will be just about the right amount of time. So we're looking at tableaux that look like this. And the overall question is, like, what features can we identify here that, well, I guess, how can we express this condition, not in terms of just a formal count, because actually I prefer not to prolong if I can avoid it, but just if you give me a table, a vector space of matrices written in this form in some basis, and maybe you like blur out a corner of it, can I fill that in to make sure that it's involutive? In other words, can I choose, say, how big these are, then gradually fill in the pieces below so that this condition is guaranteed to hold at the end? So in order, can I build this iteratively to guarantee that condition? That's the third question I had in the war at the beginning. So here's how this goes. You could look at a point here in the tableau and ask, okay, so let's call this point pi ai. So this is row A, column I. It looks like it's L, but it's somewhere over here. And I know that because it's, if it were up here, it would be independent. If it's below sort of this demarcation line of independent things and things that depend on them, then this must be some linear combination of all of the things up there. So in other words, we can simply write this as, okay, so what is it? So we can write this as pi ai is equal to some coefficients So the B's are just a big pile. So it's got 4 coefficients because it's a matrix term with respect to a matrix term. So it's just, it's just that many coefficients. It looks a little ugly. It's not really worth thinking about it as a tensor. It's just a big pile of coefficients indexed by multi-index. And let's see. Let's suppose that I want the sum to be over things. So it has to be things where B is less than or equal to S lambda, and lambda is less than or equal to L. Right? Because those are the ones which are up here. The SLs are the lengths, and L is how far over you can go. So anything sort of down below depends on the things up above. And that's essentially how Dean Yang approached it, and it was successful where we wanted to do. But I was kind of looking at this and thinking, well, why don't we just flip this around? It's a very basic thing to do algebraically, but what we'll do instead is realize that each column of this is taking values in some space W, in the space W, which is where columns live. So what we can do instead is we can write, this is a really dumb thing to do, just linear algebra, is say, let's see, how does this column become that column? In other words, what is the map from this column to that column, right? Well, you can just flip that around and see that the A's and B's are simply, the A's count, the B's count down this and the A's count down this, if I fix lambda. So this map here is what you might call B lambda I, which has coefficients which, A and B are running down the terms, but so B lambda I is a matrix. So each is an R by R matrix. So once you're at that point, you just ask, well, okay, so let's do a giant proof by induction, right? If I have a matrix with one column, I'm done. If I have a matrix with two columns, I ask, I've got the B1,2s, and I ask, what do I have to check in order to have the Cartan test apply, right, to have it pass? So you write down that equation, it's ugly, and then you do it again for 3 columns and 4 columns, and you have Sage or Mathematica or something help you as much as you can, and you start canceling terms to say, oh, there's a pattern here. That's your inductive hypothesis. You prove it by induction. It's, 6 pages of horrible arithmetic? But it's just arithmetic, right? So like, once you see the right inductive hypothesis, proving a proof by induction is usually easy. It's getting to that hypothesis first. So I think I just kind of pushed it far enough that you could just write it down and then observe that it's the right thing to do. So here's the condition. So let's say the theorem. Okay, so the tableau A is involutive if and only if. And I'll discuss some of the conditions if we have them met. So there exist bases of W and B such that, okay, so there's 2 different types of conditions. There's linear conditions and quadratic conditions, and nothing higher, which is sort of nice, right? Not too surprising there's nothing higher because it's about wedge products, but still nice to see. So B A lambda I B is equal to 0 for all A bigger than S lambda. So what that's saying is that the things so if this term, if I look at how these generators go over here, everything below here is zeros. This column, there exists a basis in which this column cannot affect those terms. What that effectively means is that if you look at S1, everything below that line is zeros. That's like we had the first row of zeros up there, which you say it doesn't matter when you're looking at the ideal. It's just killing some variables, and you rewrite your system in fewer variables. But even more so, this can only affect up to there, this can only affect up to there, and so on. This last one can only affect over there. So it sort of is pushing things upwards. So these are all of the linear conditions. And the next thing is sort of interesting. So B lambda I, B, it's both interesting and boring, which is why it's interesting. It's actually really boring, but the fact that it's so easy is why it's nice. Okay, so each of these is an R by R matrix. I can make this composition. This is what this is really doing, is it's skewing on the output variables. Right? So I just flipped ij for ji. I want this to be 0 for A bigger than Si and some other technical conditions I need to write down. A is less than I is less than j. And lambda is less than mu is less than or equal to j.
And AB means you insert that in all 4?
Yeah, so exactly. Well, you compute this matrix and then look at its rows. So this is, AB would be the 8th row of the bth column of this R by R matrix. So everything. So yeah. So it would be great if these conditions weren't here, because this would be a commutativity condition of matrices. It's not quite that though, because it only has to commute on certain subspaces. And those subspaces can be defined in sort of a formal way that obviously I'm not going to do in the next 3 minutes. But the reason that this is sort of a neat result though is not so much that, Guillemin proved very clearly that something like this must be true. There must be this condition where you look at sort of commutativity on certain subspaces. And he actually only looked at it from here over and didn't really deal with this mess down here, which is why all these conditions are necessary. But he definitely proved that involutivity is essentially about commuting on certain subspaces in the right way, and he made that very precise. But the great thing about this is that you can type this into a computer algebra system. And so saying that there exists a quadratic ideal isn't the same as saying here's the quadratic ideal, right? Okay, so for all you guys, so here's the next step, right? Well, I'll basically end here. So here's the next step: is I have code that I've been writing for Sage. That URL in case. So if you go to, so I have Bitbucket, which is a code sharing system similar to GitHub. So if you go to this address, there's the code for this package I've been working on. I haven't worked on it much since the winter, but I'll pick it up again in the summer. But what it can definitely do now is, it does all this computation. It's a system which defines how to work on symbols in Tableau, but it works on them using all this language of Spencer cohomology, and I didn't even talk about characteristic varieties, but that's all embedded in this also. It's actually the same rank 1 condition we're using over there on this, and you can compute it in terms of these. So but the thing is that you can tell it to say, build me these equations for all the Tableau, say pick R, pick N, pick S1, S2, S3 up to Sn, and say build the ideal, right? And it will just spit it out like 25 seconds later, right? So that's something which so far, right, the only thing we really understand for PDEs is PDEs in 2, maybe 3 variables of like first or second order, right? Like that's all we can really work with, to be honest, in terms of like formal theory. And the dream that I'm hoping this is going to help with is that, so here's the overall general picture, right? So here's all PDEs. Or actually, let me be more, this is all Tableau. So it's fiber-wise all PDEs. Okay? It's the fiber of the space of all PDEs. Okay, so sitting inside this is some subvariety, and we know it's a subvariety defined by quadratic equations. Quadratic and linear. And linear equations actually are really, these linear equations are so easy to get rid of. That's really a purely quadratic condition. And actually, one more thing I should say is that because these were generated inductively, I haven't proven this, but because of the way they were generated, it seems very likely that these equations are actually independent generators of the ideal. So it should be sort of a minimal basis. So in here, you've got the involutive ones. And so we've got an ideal, which describes that subvariety. So here's some very basic questions. If you say, I want to look at PDEs in 3 independent and 3 dependent variables with S1 equals 3 and S2 equals 2, how many are there? Right? What's the dimension of that variety? Very basic question. What's the degree of that variety as an abstract variety? Not, obviously it's ideal is degree 2, but that's true for every variety, as we know. So that's maybe not super interesting. But the fact that, so what's the dimension of that subvariety? And the other thing we know is that there, as Dean Yang proved, there is this very well-defined subspace. There is sort of a hyperbolic, which some of them are involutive and some of them are not. And so these are the ones that Yang studied. So those should be a subvariety of this variety. It should be a clear algebraic subvariety, right? Moreover, we know, this is not as strong, this is sort of not written in the phrasing of Dean Yang's work, but one hopes that there's something like, take Neumann and Nuremberg notion of ellipticity and have sort of a generic elliptic theory for things, and you expect that to be somehow like, there. And then there's maybe some parabolic things, right, where they intersect. So so this is really the point is that, okay, so now we have an ideal. So this is the ideal for an interesting variety. And maybe actually, let me rephrase this. This is actually like, oh, and this variety is really, what's the right thing to say? I mean, I really want to use the word moduli, right? We're trying to decompose the moduli of all tableau, and particularly of involutive tableau, and see how they're structured. It's very easy to write down all the examples by hand, and 2 by 2 or 2 by, well, even 3 by 2 is getting hard. So 2 by 2 you can do it. Right? That's an exercise everyone does. But even 3 by, I don't think anyone's written down like just point-wise with constant coefficients. What are all the constant coefficient 3 by 3 tableau PDEs? Like, I don't know, right? So this is something that could definitely be checked by getting some grad students who can do computer algebra a little bit and know about things. There's a whole bunch of software that does numerical algebraic geometry. So you can do things like compute dimension and degree quickly without having to go through all the Grover basis stuff, which can be very slow. So the next step is take this thing, apply all the great tools from Grover bases, look for subvarieties that are particularly interesting, see if they're find the singular sets. All the standard questions for varieties are now can be applied to these involutive PDEs. So hopefully that leads somewhere. It's got to, right? So, all right. I guess that's all I have to say. So thanks.
In terms of the counting of how many there are, it looks like that because when you do the prolongation A and A1 and A2 and so on, do they count as different ones?
Oh, yeah, that's an interesting question. So once A is involutive, all of its prolongations are involutive. Right. Yeah, so this will not overcount because, in fact, what will happen is that, so the thing I didn't even get to, because that would be another hour and a half, would be talking about the characteristic variety. So characteristic variety is exactly the generalization of the characteristics here. The thing is, it's a variety. It's a variety sitting in V, in PV. And once a PD is once a tableau is involutive, all of its prolongations share the same characteristic variety. It's isomorphic. And these equations reflect that fact. So
what I'm saying, so these equations for A and for A1 and for A2 before.
So what I'm saying is when you write down the tableau in this form, it is normalized.
Oh, you're talking about the last one. Then.
Yeah. So when you write down the tableau in the normalized form, other than a bunch of rows of zeros, it will be identical to the ones of its parents. So once something is so all you'd be doing is adding more zeros, which doesn't change the number of solutions. Okay. Yeah. It doesn't better than bigger space.
Okay. So that means if I start with a system,
right?
I have the A. I can't. Okay. So, all right. Then I'll look at these B's and I'll know whether it is involutive or not, and then if not, I prolong and so on.
Right. Yeah, so this isn't quite to the point of parameterizing them, but it's getting close because once you have an ideal, you can look at parameterizations of it. So, again, that's something that has to be done in algebra software that I haven't gotten to yet. But. Any other questions?
But so is this? Well, this is good for constructing involutive system. But the Capon theorem already tell you when.
So it's true that this doesn't add anything so much directly to the theory of what solutions look like when. So here's why I think, and these are actually very straightforward to write down once you sort of see how to approach it in terms of linear algebra. I think the reason that these were not by Guillemin directly or by anyone since then, I mean, that's a big gap for a very simple result, right? So why is this such a big gap? Because so people like, people like Robert Bryant, people like Phil Griffiths, right? So what they do is someone gives them a PDE or a geometry, and they say, I came across this equation in physics. Does it have solutions? And they have an equation, and they use Cartan's test, the family of all nearby equations. They were given one equation to examine, and they examined it and found the answer. Maybe they constructed some solutions explicitly for that equation. The other side is people like Guillemin and Sternberg and like the whole sort of family of, and Quillen certainly, and the whole sort of family of very, I think, very sort of hard-hitting algebraic geometers who want to construct a beautiful formal theory that they know works. So they don't care about coordinate or about local descriptions at all, because they want to know about exact sequences, and they want to know about kernels and co-kernels and cohomology. Like they're doing very formal computations very big, right? So this is somewhere in the middle. So this is it's about examples, but it's about a family of examples. Whereas I think so far people have either looked at one example or the entire problem as a well-defined problem, and this is somewhere in the middle. So I think this is why it's sort of always like people would sort of get really close to this and then almost veer around it because they want to do something else. But so the question I would like to answer is like, if you give me an equation which so here's why this might be applied. I've been talking with some like physicists and engineers recently. Suppose you give me an equation that you think models something that you've been working on, and you say, does this have formal mathematical solutions? And you can answer yes or no using in the analytic categories using Cartan Keller. But then you can have this feedback where you say, well, that one does, but also here's a one parameter family of nearby equations that have the same type of solutions, but have a slightly different shape, right? They're maybe have more curvature, they have just slightly different invariant, like the invariants work slightly differently, right? And that way you can start saying, well, okay, so not only do we have, this is the dream of people who work on integrable systems, right? We love the wave equation. Everything that people call integrable really is like something that's sort of like the wave equation, but not quite, right? So like, can you start the wave equation and sort of see what's nearby in this variety by taking the local like studying the wave equation and like taking a local parameterization near it to see whether Tableau have similar structures. So that's, I think that's the sort of thing that would be neat to play with. I don't have any answers yet, of course. That's a big, long-term sort of discussion, but that's, I think, the direction that the vector is pointing.
Well, that's what I was thinking when we talk about deformation.
Yeah.
And of course, the argument you suggested, really it's a deformation. I can start from the point, first order, second order, third order solutions. Yeah. But now, if you have a solution, you can then ask about deforming that solution. Yeah,
so one thing I found this winter that was sort of fun was I just sort of almost, so something you can do, I don't know if this is useful, but it's sort of a neat idea, which is along the lines of deformations. Okay, suppose you have a PDE, and it has an involutive PDE, and it has a solution. Okay, so this whole structure of A and the whole tableau, pull that back to this. You have a vector bundle over a particular manifold, and that vector bundle has a lot of structure in it from these equations, and then you can start studying the symmetries of that, and you can get a new G structure over this manifold, some new principal bundle over this manifold, or some you get some bundle of geometry over the solution manifold, and now you could ask. What you have is sort of what you'd call maybe an annotated solution, right? So you have a solution with information about how it was built, but not the details of the PDE it actually solved. You could ask, how can you take that solution with that sort of initial data and ask what other PDEs could it solve by varying those in sort of normal directions? That's sort of interesting question, exactly on the lines of definition. I don't know if that's useful for anyone, to be honest, but I think it is sort of a neat thing that's like bring this back to the original, its original source, which is sort of G structures and geometric invariants. So,
how much dependence are there, let's say, in real problems, when the initial conditions are given or initial conditions are given, depending on numerical values?
That's a good question. So the people
that would be, you know,
the people I know who do numerical
something that's useful.
This is the thing that's sort of disturbing about this whole field to me is that the people who do numerical PD, any of them who actually care about solving things, right? Now they care about solving things. They know usually is to take a PD like a Lagrangian formulation on which we have much more powerful computational tools because you can have concrete conservation laws and use sort of symplectic tools and also conjugate you on energy equations, on flow equations, and then you look for like weak solutions, right? Because maybe the interesting thing computationally isn't the analytic part; it's the part where it's not analytic, and so they want weak solutions, and so they're looking for a thing for numerical methods that can identify, spikes and distributions and so on, and things like shockwave equations, crystal equations. Because the numerical people I know that are really interested in those things is when certain KR theories, it's both a set of measured one, a fact, right? So they're interested in the. So I say, generically, you have analytic solutions depending on three functions of two. They're like, okay, you can have constant rank and all those. All those forms. How does pure math?
Are you